Good afternoon to one and all present here. I welcome all the participants to this Phase 4 6 days short-term training program. Now we are going to start this fifth day and second session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. A. Ajay M. Sidpara, Professor, Indian Institute of Technology, Kharagpur. He has completed doctoral degree from IIT Kanpur. His interested research fields are development of nano finishing process for complex surfaces, magnetorheological fluid-based finishing. He has published more than 180 research articles in international journals and conferences. His citations are 956. H index is 16, I-10 index is 17. He is the life member of ISTE and AMM. He has completed 4 sponsored projects. He has obtained 2 patents for the benefit of society. He is having many honors and awards, and here are the few glimpses. Institution of Engineers India Young Engineers Award in 2015. Gandhian Young Technological Innovation Award in 2013. He has received research funding under Young Scientist Research Award from BRNS in 2015. We welcome you, sir. We are honored with your presence, sir. The current topic is mechanical micro machining. Now I request our resource person to proceed with the session, sir. Requesting, sir.
Thank you very much for your kind introduction, Professor. So in the last lecture, or probably the last time when we interacted, at that time I introduced surface metrology related things, that means measurement. And today we are going to discuss about the mechanical micro machining. Let me share my slides.
Sir, your slide is visible, sir.
Yeah, thank you.
Yes, sir. Yes, sir.
So mechanical micro machining, why this topic I have chosen, because now if you see that I think around 10-15 years before, whenever we want to do machining at a micro scale, mostly we think about the EDM process, ECM, laser, electronic machining, and all this. Like that means all non-conventional machining process or advanced machining processes. But if you see nowadays that this particular mechanical micro machining, that means the machining at micro scale using milling machine, lathe machine, like that.
Sir, sorry to disturb you, sir.
Yeah.
We are seeing the next slide also, sir. It is not like a full presentation mode, sir.
This is right now it is first slide. Which slide are you looking?
No, first slide only, correct, sir. But we are seeing in the side, next slide references like that. It is coming. It is not the view. It is not.
Okay, understood. Understood.
Yes, sir. Yes, sir.
Understood.
Yes, sir. Now presentation mode it is better, sir.
This looks better, I think. Then.
Yes, sir. Yes, sir. Presentation mode better, no, sir. Presentation mode means like that it is coming. Okay. Previous thing is better, sir.
Okay.
Okay, sir.
Sir, excuse me, sir. Sir, there you can change some options, sir. May I, sir?
Yeah.
Sir, please you go to presentation mode, sir.
Yes.
Presentation, yes, sir. There you can see that 3 dots with a circle display.
Yeah.
No, on the bottom, sir, in the bottom. Yeah, that thing. Hide presentation. Screen, you go to screen, sir. No, sir. There you have to go to screen. Yes, sir. Yeah.
Now it is okay.
Now it is okay, sir.
Yes. Okay. Yes, sir. Perfect, sir.
Thank you, sir. Thank you.
Yeah. Thank you very much.
Thank you, sir.
So now if you see that because of the there are a lot of advantages and some of the recent advancement in the machine tool building, that means the way people are making the machine tool like milling machine and lathe, now there are a lot of advantage of using this conventional machining processes also at the micro scale. So only thing which is right now also challenging is the fabrication of micro tools, because right now if you say that if you do normal conventional milling machine or lathe operation, let us target only or focus only on the milling machine, because you can easily get 5mm end mill cutter, 10mm end mill cutter, but now you can think that suppose end mill cutter is around 100 micron along with the floats and everything. So That is really challenging. So machining of micro scale components using our conventional process like milling and all these things. So at that time, some of the challenges are there, but still people have started building machines which can work at the micro scale as low as around 20 micron or something, because right now people have already developed some cutting tool, that is end mill cutting tool up to diameter of a 10 micron also. So let us see that what are the challenges and what things we have to look into it when you do machining at micro scale using conventional milling. Conventional milling, that is milling process, not conventional machine. Machine will be different, but the process strategy and the programming, everything is almost same like the conventional. Whatever GNM code we are using, same way we can use it. And if you see this particular slide, there are many components are there. So these things are, if you see this particular first figure is the EDM tool. Now, if you see that if you are using electrode discharge machining for micro machining and you are using die sinking only, that means your tool is not rotating. It is just plunging up and down. So at that time, what you need, if you want to create some features, you need reverse features on the tool also, correct? Electrode, that is what we call. So for making those electrode, again, you have to come back to this mechanical micro machining. So electrode discharge machining is not an independent process. You always need support from other processes. It is not necessary you always go with the micro milling or something like that. You can use some other process also, but you need a tool with the same features which you want to replicate onto the workpiece. So that is the reason that is not independent process. Second thing, there are a lot of small components are there, gears and some type of sprockets and everything. Third one is the one type of a medical plate that is used to hold the broken bone in your body. So you can see the size is very, very small, maybe around 20 millimeter or something, and you can see small features. And last one is the some type of micro pillars fabricated, and you can see the matchsticks along with these dimensions. You can understand what is the size of the dimension. So all these things are fabricated using mechanical micro. That is mostly the mechanical micro milling process. So these are the further reading. That means I have taken many things from these particular books and all these things. But more important things are these three websites, because we know that when we refer books are not actually updated the way they are updating the websites, right? Because once you publish a book, it will take years and years to get the second revision or something like that. But you can easily update the websites. So these are the three websites mostly we target. So this is the modern machine tool, and this one is the cutting tool engineering magazine, and this is the production machining. So if you visit this website at least once in a week or something, you will always find some type of new development in the micro machining field. So it may be connected with the EDM or non-conventional processes, but it is also for this particular mechanical micro machining. So these are very good website references where you can get very, very highly updated references, and you can understand that where the things are going right now. And obviously, journal paper, product brochure, these things are obviously there. So now, first we have to see from the basic. That means why it is difficult to cut at micro level using our conventional milling machine or the lathe machine, right? Because we need something from three different things. So what are these three different things? You consider one is the machine tool, another thing is the workpiece, and third one is the tool. Now, is this simple example is the cutting vegetable, right? If you can consider that if you are cutting tomato and if you are cutting potato, there is little difference, right? Because tomato is soft and you have to actually move your knife to and fro to cut the tomato. But if you are just pressing the knife in the potato, then sometimes you can cut also. You don't need to reciprocate, right? That is the reason, because this soft material needs some type of shearing, then only it can be machined. So material point of view are also there, because sometimes you have machine tool also, you have cutting tool also, but workpiece is some different type. At that time you have to think something out of the box solution, then only it can do. Second thing is the cutting tool. Now you can see that you have very sharp knife and another one is a dull knife. So at that time, dull knife, you have to apply more force, or you have to, it is taking more time to cut the material. So for same thing happens in case of micro machining or the conventional machining also. Sharpness makes huge difference, but the sharpness does not last time, because we know there is a one term that is called tool wear. Because as soon as you start machining, your tool wear starts, and after a certain time, it is so high that you have to stop your machining process. If both the things are okay and you do not have a proper machine tool, that means the proper rigidity, stiffness, then process parameter setting, resolution, position accuracy. So these are the things related to the machine tools. So you require all these three things. Workpieces also should be machinable at a micro scale. You should have a very enough size. That means the whatever dimensions you want to cut. Suppose you want to cut 100 micron channel, then you should have a diameter also 100 or less than 100 micron. Then only you can cut something like that. Tool is required which can allow you to hold this 100 micron tool and efficiently cut the material. Otherwise, any of these three is not, then you cannot cut anything at a micro scale. Correct? So let us take simple example that if you see the milling machine operation, this is also doing something not exactly at the micro scale, but maybe at a 1 millimeter scale or something like that. So in this case, what is the thing that once you do machining operation at micro scale, one biggest challenge is that it is not possible to visually detect the changes. Changes in the sense that suppose your tool does not have any signal by which you can understand the tool is broken. But if you see our normal conventional milling machine where you use 5 millimeter tool, 10 millimeter tool, just breakage of the tool, you can sense that something is broken or something is going unfavorably. Maybe some heat temperature is very, very high, some fumes is coming. So though there are many indirect indications by which you can understand that something is going wrong. But in micro machining, since the size of the cutting tool and the machining domain is so small, that unless you use some type of a indirect sense, that means that by using force measurement, by using some type of a other acoustic signal, you cannot find something is going wrong or it is going as per your requirement. So that is the biggest challenge. So that is the reason whenever you see this micro machining, it is always coupled with a dynamometer. The dynamometer will give you some information indirectly, not exactly the tool status, but if something is going wrong or something tool is broken, if the tool is broken, that means there is no contact between the tool and workpiece. And if that happens, your signal of the forces will be 0. So after a certain time, if the signal goes suddenly down, you understand there is no contact with the workpiece. Reason may be anything. Maybe tool breakage is also there. Maybe your part program is written incorrectly. That means it should be in the workpiece, but your tool is moved away from the workpiece. Many reasons are there. But you understand that your tool is not doing anything with the workpiece. So that indirect indication is possible when you are using some type of sensory element. Correct? Same thing happens for the turning operation also. Because if you consider in our conventional turning operation, you tell the students that you take a 10 millimeter diameter of the rod and try to reduce as small as possible in conventional machining operation. Right? So let all the students will do this kind of work, and then let us see that which one is coming with a small diameter. Doing turning operation, then what we do that we slowly remove material like this. Correct? In this way we reduce the diameter. But after a certain time, what is going to happen that your tool diameter is something like this. Up to this we have already removed. So this thing we have removed like this way, and once it is reaching a particular way, it is not possible. So now we have to find out why it is not possible. What is happening? Where is the problem? Why we cannot reduce the diameter maybe around 500 micron or something in conventional machining? Whether it is a problem of the tool, it is a problem of the workpiece, or it is a problem of the machine. And at the end, you will find out it is problem of all three. None of these things is suitable for a particular operation. Workpiece may be suitable because sometimes what you use high purity workpiece material, that means workpiece you may omit at the end. But the tool and the machine tools are the two major problems where your conventional machining process cannot go beyond a certain limit of the machining. So that is, we will see today that what are the things we have to look into when you do machining at a micro scale. So first we have to see that why machine is not capable to do machining at micro scale. What are the problems? So now if you see that your machine is basically the kinematic manipulator. That means there are many axes are there, many joints are there, and all joints are actually coupled with each other. That means your X, Y, Z axes are coupled with each other. If you see this particular thing, that this particular thing, X, Y, Z, three thing axes should be exactly perpendicular to each other. Correct? If this perpendicularity are not there, then you are adding one additional problem that is called the straightness problem. But we see that how this is making difference. Now you can say that there is one joint here, one joint is between the slides and the base, and then from the top of that there is consider this is the y-axis, then this is the x-axis. These are coupled with each other. On the top you put vice, and on the vice you put fixture and workpiece and all this. So these are basically joints. Now consider if some problems are there in the joints. Which type of problem? Problems are the connectivity problem, that they are not firmly fixed with each other. So these are the X, Y, A, C, and the cutting tool. So these are the things. So consider it is not firmly gripped with each other. There is a problem of the perpendicularity. Your X and Y axis are not perpendicular to each other. There may be a little bit of problem. And the problem is that your tool or the chuck, whichever you are using here, these are not concentric with each other. That means this is considered the axis of your spindle, and your cutting tool axis is a little bit shifted from the axis. Our objective is the both should coincide. If these are not coinciding, then there is a problem. This is called run out. So there are many other ways by which you can, that means machine will introduce some errors in your machining process. So that we have to see. So these are kinematic manipulator connected with each other. So what are the problems? Problems are that if something is not working fine, then the whole system will fail at the end. So you have to ensure that all the things are perfectly working and they are performing their own duty without any problems. So there are revolutionary joints are there, cutting tool and workpiece are the main points where your machining is being taken. So our area of interest or area of region is this one. Rest of the things are the supporting system. Whatever we are looking at this location, these are the basically supporting system, right? This will remain as it is. Only thing what we change the workpiece, because we have a variety of workpiece. And for different type of variety of workpiece, we have different type of cutting tool also, correct? So that is the variable, but rest of the other things are the stationary part of the machine tool. There are linear slides are there, structural elements, connecting joints, actuator, sensors, all these things are there. So our objective is that we have to make sure before you start machining operation that everything are working fine. So you have to give a checklist. Once you see that everything is working fine, then only you attempt for a micro machining. Otherwise, there is 100% chance that you will not get the required results. That's all. What is the important thing here, that when you do machining operation, our area of interest is this machining zone where it is being done. So if you are ensured that your cutting tool, whenever it is in contact and it should move in this direction to cut the material, correct? And this is rotating in this direction. So if you are able to move this material without any problem, that means everything is working fine. So from kinematic point of view, only one function of the machine tool. What is that function? Accurately and repeatedly control the point of contact. So what is the point of contact? Point of contact is this one, where your tool is touching the workpiece surface. If you can control that point to a very, very low level in the sense that a micro level or the meso scale, the way we are cutting conventional machining, that means you are getting results without any problem. This is simple example. This is your conventional machining operation. This is your CNC machining operation. Not exactly micro milling, but at a automated. That means you are using GNM code here. So how these things are different? Because difference in the sense that operator is operating this particular machine, correct? Because 100% operator attention should be there, starting from putting the workpiece here, putting the cutting tool here, then moving the cutting tool, measuring the dimension. Everything should be done by operator. That means 100% control should be with the operator. What is happening in this case? Operators coming into picture at the time of writing GNM code. Once GNM code or the machining program is written and it is fed into the machine tool, after operator's work is zero. Only thing, he can observe the process. By chance something is going wrong, he can immediately press the emergency button and stop the machining. And that is the only thing. But in terms of operation, he does not have any type of role. So what is the advantage? Advantage is that the repeatability and quality control is very, very high because everything is done by the machine. Unless there is a problem in the machining drive or the linear axis and all these things, then their problem might have entered inside the machining operation also. But that is not the case. Here, what is happening that in the morning when one person is coming into machining, he is fresh, he can do machining very quickly and efficiently. But the same person is continuously working for 5 or 6 hours, and at the end of the day, when you are even is machining the same component, there may be a huge difference in the quality. The component is fabricated on the first half and component is fabricated at the end of the day, because fatigue is there, monotonous work is there, because we do not work the way machines are working, right? So that is the reason that it is very difficult to do machining and everything at a very low level or very low dimensional level in case of a conventional machine. Right? So all other function, that means to control this interface between the cutting tool and workpiece, all other function, that means the machining operation, structure of the machine tool, they will help to maintain this interface. So our objective is that when tool is touching the cutting workpiece material and cutting the material from that, at that time it perfectly retain its position. So for retaining its position, you need very, very firm backup from all the things, correct? Because there are forces generated. Now consider this is the cutting tool, this is the workpiece, and workpiece is rotating in this direction, and you have cutting tool here. Right? So when it is rotating, at that time, consider your depth of, you have unknowingly you have given very huge depth of cut. To remove this much amount of material, your spindle on which your tool is, that means there is one motor here at the end on the head structure which is rotating your cutting your workpiece. So if your motor power is not so high so that it can overcome this friction or overcome of this particular depth of cut, then your workpiece will stop rotating. Correct? So that is a problem. Even if consider that motor power is enough, but you have entered your workpiece or penetrated your workpiece so high that if it is rotating, your tool will be broken from here. So there are problems, correct? So whatever small depth of cut you are giving, at that time you have to ensure that your motor power is enough to remove or rotate at the same RPM. Cutting tools is also strong enough to resist the cutting forces and maintain its sharpness for a little more time, so that you can use the same cutting tool for the next operation also. Otherwise, you have to discard and you have to use the fresh one. That's the biggest problem, is that we have to avoid errors. What are the errors? Errors are basically the position errors, contact errors. So if you reduce the error, that means you can do cutting at any small scale. So there are forces generated. Forces are because of the cutting forces. Weight of the structure and element themselves. So these are the static forces. This is called dynamic forces. Dynamic forces, that means forces generated when you do machining. Static forces, that means the structural forces. That means you have a machine tool structure, something like this, and from here you are holding your cutting tool. This is the cutting tool, and on this particular side you have workpiece and something, and then it is doing machining. So whatever this overhanging portion is there, by chance supports after so many years, what is going to happen? That you will get some type of structural deformation. So now your cutting tool may be something like this. Correct? So because it is not exactly perpendicular to it, the same thing happens in this side also. That means these are the structural deformation. It should not happen this way. Yeah, so this is what it is showing. This is the one common diagram where it is showing that what are the things you have to pay attention. So how things are working? This is your machine tool. So initial starting is the part program. You write part program in some other computer and then feed into this particular system. So there are two things. One is the data processing unit, another is the control unit. Control unit has work when you are getting some feedback. And when data processing, that means you are putting a part program into the data processing, it is generating motion. Motion means X, Y, and Z axis motion. That motion is transferred to the driving system. That means there are either stepper motor is there, servo motor is there, which is driving your X, Y, Z. This driving system will go to the machine tool. It is inbuilt in somewhere here in this case, and then it is moving the axis. So axis movement is the only thing. Rest of the thing is done by the cutting tool. So once cutting tool is moving, at that time it is giving feedback. Which type of feedback? It is giving two feedback. One is the position feedback, another is the velocity feedback. So what are these two? So you are starting something like a 0 and you want to reach to this 10 mm. Correct? So when it is moving from here to your 10 points, so this is particular thing is called the position feedback. Whether it has reached to the 10 millimeter or it has reached to 9.99 or it has reached to 10.01. So this particular feedback is given by the position feedback. And another thing is that in what is the time in which it has reached to this thing, that is the velocity. So that is given by the velocity feedback. That means from 0 to 10 millimeter, it is reached to that location or not. And if it is reached, how much time it took to reach to this location. So these are the two things. So position and velocity feedback will go to the control loop. If some problems are there, then it is going with the, again, machine tool. It will refine the program and again it will do the same machining operation. So where we have to pay attention? We have to pay attention at this location, because it is giving feedback, it is giving some information from the machining joint, so it should be reliable, correct? So to get this thing, you need some feedback devices. So these feedback devices are called encoders. There are rotary encoders are there, linear encoders are there. Other than these two things, there are 4 sensors are there. They are not connected with the feedback or for position or velocity, but it will give you information about the status of the machining joint, right? Then you have to spend more money in the driving system, because driving system should be very sensitive, because you are telling that you want to move at a micro level. So if your driving system is not giving you the motion in the step of 1 micron or 2 micron, then your machining will fail. You will not able to do cutting at a micro scale. So you require system which can move in the step of 1 micron or less than 1 micron. You need a system of a feedback system which will detect the movement in terms of micron. Right? Suppose you are telling, your system is telling, suppose you have a control system, here it is showing X, Y, Z, and when you move your axis, it is giving some values here, correct? So if you're telling that it is moved from 0 to 10 millimeter, who will tell you that it is actually moved there or not? This feedback system will give you that, yes, your actual system has moved from 0 to 10 millimeter. So if your feedback system is not reliable, then there is a problem that it may give you wrong feedback also. And wrong feedback, that means your system will collapse at the end. That's so what are the machines? Because these are the machines. I think I collected this this particular slide long time before, maybe 3-4 years before. But now many people have, many companies have introduced new machines. So these are basically the micro machining. So the micro machining in the sense that you do not expect that these machines can do machining over a large area. Large area in the sense that 2 foot, 3 foot like that. But they do machining at a very, very small scale and very, very fine features. We will see some of the examples where you can see that these are very, very fine features generated, and it is very difficult to get if your machining, your machine tool does not have any type of supporting system. So Kohn, EVOS, Chodik, then these are mostly the German, Japanese companies are involved. European companies are also there, PCTech and the Moore Technology, Kugler and all this. So you can see that these are the machines available. We have these particular machines in our manufacturing department, manufacturing lab. So how these things are different now, let us consider between 3 things. One is the conventional milling machine and the CNC milling machine, and then CNC milling machine with the whatever picture we have seen in the last diagram, that is kind of milling, micro milling machine. So let us see. So these things are not feedback control, because these closed loop controls are there. There are CNC machines where you do not have closed loop control. So these are open-ended. That means if you use a stepper motor, then just by knowing the steps of the rotation, it will generate a signal, but it is not basically feedback. So you have to believe that your tool has moved from 0 to 10, but there is no secondary system which will give the same information. That is called feedback. So you have CNC machine without feedback also, with feedback also. Control program, because here we write GNM code, but here everything is depending on the operator. Accuracy of the slides and guideways, there is hardly any difference, because obviously you require straightness and perpendicularity, everything here also. I mean, it is not like that these systems are not accurate. These are also very accurate, but only thing that the operator is the person who will decide the part will be quality made or it is there some type of a rejection of the part. Automated operations are there. Obviously, this is related to this, and structural stabilities are required on both. That means in all the machine, obviously structural stability is required. Now coming to the difference between normal CNC machine and the micro milling operation. So where there is a difference, if you see the size, shape, everything is same. If you see the spindle here, spindle is also here. You have table also here. Table is also there. You have part programming, control panel is here also there. I mean, there is look-wise there is no difference at all. So where difference is, the difference is there in terms of movements. That's a closed loop control system. So whatever you are using here, you are using feedback control here. It may be 5 micron steps or 1 micron steps. But this 1 micron, 5 micron steps are not enough here. So what you require 0.5 micron steps. That is for the encoder, whatever linear encoder you are using, rotary encoder you are using, because smaller is better in this particular case. So that is the reason cost is shooting like anything between the normal CNC machine and the micro milling machine. Accuracy of the slide and guideways, what in terms of which accuracy? That means it is in what they do, that they do machining of that particular cavity, whatever cavity is coming, and that cavity is used as a mold for the particular cover. So for that you can get, for micro molding operation, there are many different type of dies are required. So these dies are created by micro milling operation. There are lab on chip or the microfluidic applications where you require micro channels and micro mixtures. Dimension may be less than 100 micron also. So for that you require micro milling. And not only micro, there are other processes also there, but micro milling is one of the processes which can be used for making these components. So biomedical, biomems products, then tool surgery, medical implants, lab on chip, dental brackets. So these are the different applications, and these are the turning operation. Micro turning. You can see there with the size of the pencil sharpness, then you can see what is the size of this component. So these are all fabricated using micro turning. An old age example is the watch case base. If you remove your watch and then you open it from the base, you will see that there are a lot of small features, because here you have to accommodate gears, and then gear is also a shaft. That shaft should be perpendicular exactly, and these are small holes and small features. So these all things are fabricated using micro milling operation, because micro milling is very quick. Then another thing that you have ornament. Then for ornament, what we need a die in which your molten metal is pouring, and then it will generate the shape. So these all the things are fabricated on machine by micro milling. So these features are very fine, and then you pour the liquid mortar, maybe gold, silver, or some other precious metal, and then it will take the shape of this. So these are the very old age example. People still this, there is no any type of match with this particular process as compared to conventional machining processes. Automotive, now you can see the injection nozzle means there are hundreds of applications are here. So if you see that there are many sensors are there nowadays. If you see car, you will find less amount of manual operation than the most of the operations are the automated operation. Even now driverless cars are also coming. So these are the things where you require a lot of sensors, and you know that sensors are not very big in the size, because now you know that you cannot increase the size of the car just by introducing a lot of sensors. You have to make sure the size of the car remains same, but you can introduce your sensor in such a way that it is not creating too much of inconvenience during the assembly of the car. It should accommodate sensors within small regions so that it cannot interfere with the other components. So basically that you have to play, or you have to accommodate everything in a confined area. You cannot increase the size of the car just to introduce more and more sensors, right? So that is the reason the size of the sensors are also very small. And that is only possible to fabricate when you are doing machining at a micro scale. Right? So in this case of a micro injection nozzle, you can see that there are a lot of holes on the outer periphery here. So these are the holes where, because of that, your fuel will be spread in all the directions. So you will get uniform combustion in the combustion chamber in place of just passing of the fuel from the single location. So that will not give uniform combustion. So this is the micro tool for the microidium process that is also fabricated by this particular tool. In aerospace application, there are many. So this is the pressure pop. You can see this pressure pop that one person is holding in his hand. You can see the dimension is very small. This is hardly 5 millimeter or 6 millimeter. You can see that what are the features are fabricated in this case. This particular thing is a micro impeller that is used to control the flow rate at a micro level or less than micro level. Here also you can see this whole thing is maybe 3 millimeter or 4 millimeter, and you can get all these fins and everything. Right, and this is the compressor. You can here also you can see that the size of this particular thing is around maybe 20 millimeter or something. This is the overall size, but if you see these fins are very small, and that is also fabricated using a micro and mill cutter. So you can see that there are a lot of materials are there, lot of shapes are there, and that is the biggest advantage of using the micro milling operation. Because if you see EDM process, you cannot fabricate this particular thing by EDM process. But it is very difficult, even if you attempt. This can be fabricated because here you have to just modulate in the sense you have to move this component in such a way that is always coming from the top location along with the tool. That is possible, but still it is difficult. So these are the complex surfaces or freeform surfaces are very difficult to fabricate using that EDM and all conventional or non-conventional processes. And now you have seen that there are a lot of thin left, very lightweight and very thin laptop, mobile phones, everything's electronic components are coming. So for that also, if the outer body is made of a metal, magnesium alloys are used because they are very high strength to weight ratio material. So for that, what you require, initially, if they are coming with some type of a casting process, die casting or something, you always need a mold for that. So that mold can be fabricated using micromechanical machining process. And some other application there are that means the some very small scale mold for the toys and other fabrication. Then you require shadow mask for the lithography and other process, because for lithography you have to cure the resin, cure the resist, not the resin. When the light is passing through it, there are some opaque regions. So these are the opaque region. This is the transparent region. So light will pass through the transparent region and it will change the property of the resist. And because depending on that, you can deposit or you can etch out the material. Correct. And these are small engineering screw and some type of other component. So you can understand that there are many components or many type of devices where you require micro components, and for that you can use micro milling operation. Now coming to classification, because now we have seen that there are many processes which can be used for machining at micro scale. That means creating of fabrication of the component. Not necessarily that you always do machining. Sometimes you fabricate in such a way that you don't need to add the material. You don't need to remove the material, but you add the material. That is mostly right now the buzzword is additive manufacturing or the rapid prototyping. Correct? Micro machining, there are many differences. One is the subtractive. That means you remove the material. You have a big component, from there you carve out or remove unwanted material and create a shape. Second thing is additive. You do not remove the material, but you add the material at a micro scale or even a bigger scale. Third one is that you do not remove material, you do not add material, but you contain the material. That means you are deforming the material, but you are not removing or you are adding the material. So that is called casting or the forming process. And then joining material. So you have two components, you join the components. So these are the overview of this particular. So we have to enter inside. So in traditional cutting operations and advanced machining operations, so traditional, these are the turning, milling and grinding, milling and the drilling operation. Advances, there are many EDM, ECM, even if you take the combination of these two, these two. So these are called hybrid processes. So there is no end. So these are the things. Additive, that chemical vapor deposition, PVD, physical vapor deposition, LIGA, 3D printing, additive manufacturing. So all these things are called the additive manufacturing or the additive micro manufacturing. Mass containing, that means you are keeping the mass constant, but you are changing the shape. So for the forming, casting, molding, all this, and joining is obviously welding, soldering, and the bonding. So everything right now, what we're looking at a micro scale. So our right now emphasizes this one. This is the operation. In this, micro drilling is very old process because people are using drilling in the PCB and all these things. Since a long time they are using. Even doctor, dentist are also using a very micro drill bit for doing removal of micro grinding wheel, also for removing or cleaning your teeth and everything. So these are very old age applications, but our target is the milling process. That's where is the mechanical micro machining is fitting. So this particular thing is showing accuracy. Accuracy, that means starting from the precision to the ultra precision. Ultra precision, that means your component size is very big, but the tolerance is very tight. Consider that you have a plate of a, consider this is 100 millimeter. This is 500 millimeter, and the straightness or flatness is in terms of a nanometer, right? So this particular thing, if you tell that this flatness or the straightness is 10 nanometer, that means this is very highly precise component. On lower side, that means you have to increase little bit more, so that is less precise comparatively. In this particular scale, it is showing the size of the component. So this is the nanometer size, this is the macro scale, this is the meso scale, that is in between the micro and macro, and this is the micro scale. So where all these processes are standing, if you see at the nanometer scale, that nanometer scale, mostly the atomic scale micro machining and the material science, where you are looking at the atoms and everything. You go a little bit down, then these are the MEMS processes. There is lithography, etching processes, deep plane lithography. Many processes are there where you use a surface micro machining or bulk micro machining processes and you remove the material. On the lower side, ultra precision machining, that is diamond turning is there, grinding is there. So these are the processes. So you can say that if you do not consider right now this micro milling operation, something is there in between these two which is difficult to, that means no process is fulfilling this gap. That is something, suppose you have component which is considered around 200 micron size, right? So and then on the higher side it is moving from 200 micron to 1 millimeter. So when you want to work within this range is this range. So what this micro milling operation is doing, that it is bridging this particular gap. So now you have at least one process starting from mesoscale, that means in terms of a meter, macro scale, that is in terms of millimeter scale, in terms of hundreds of millimeter scale, to down to the nanometer scale. You have at least one process. But if you see, if this process is not, that there is a gap. So basically this micromechanical process is fulfilling the gap which was left, because the MEMS processor cannot be used for this particular large area, and conventional ultra precision machining also, they fail, they cannot go on the higher side, and this cannot go on the lower side. So this gap was generated, and this micromechanical machining process, it is fulfilling that gap. This gap is also fulfilled by EDM, ECM, everything, that is also still there. But right now our focus is this thing, so we are targeting only mechanical micro machine. That's a strong interest of the fabrication in this particular region. So that is the important thing. And it is bridging these two particular domains. Now coming to the operation. Now consider that you have purchased a micro milling machine. Purchasing is over. Now you have to see that how do you use that particular machining operation. That means you need a trained person to operate the machine. It is not like that the person who is operating a normal CNC machine, he has to learn something extra to operate this particular machine. Look-wise both are same, but there is lot of difference in operation of the micro milling operation and operation of a CNC machining center. Right? So in this case, what are the things? The skill based on the human hands, human sense cannot assist the process the way they do in the macro machining. Macro machining, that means the conventional machining. That consider that you are doing machining operation and there is some peculiar noises coming from the machining operation. Right? So that sometimes what happens, that the experienced person who is operating that machine for years and years, he understands something is going wrong just by listening a noise. That is enough for him to understand something is going on. So he can take some corrective action. Either stop the machining, or he can do some changes in the process parameter setting, maybe the speed and maybe the feed rate and the depth of cut, something can be done. Right? So that is possible. Or maybe sometimes that some fumes is coming, it is giving some type of the peculiar that burning smell. So at that time also the operator can sense that thing, right? Because it is happening at a macro scale, that is bigger scale. And this under generation of the noise, this type of smells or this type of smokes, it is very common, and you can easily understand that something is going wrong. But problem with the micro machining is that something happening at a micro scale, you cannot sense this thing. Because if your cutting tool is broken, who will give information if you are not using any type of force dynamometer or something like that? You continue operation, and after 3 or 4 hours of cycle, you remove the workpiece, you see that there is nothing happened. Because your cutting tool was broken on the first minute itself. You have wasted 2 hours or 3 hours time and you did not get any results. So that is the problem. If your cutting tool is getting overloaded, that means your depth of cut is continuously increasing because of some setup problem. So who will give this information? Nobody, because the is in real time, and it can act also in the real time. It can save the component from the damage. That is possible in the conventional machining operation. Detection of the problem by hearing, he can hear some noises and he can take the corrective actions. That is possible. You can do some corrective actions in the setup also. If something is going wrong, you can easily understand and you can do some type of corrective action and you can save the component. But in micro machining, what happens? Cannot benefit this kind of human element, because size or the machining zone is so small that nothing is visible, nothing is detectable. Too small scale, no change in the sound of the cut, because even if you go with a higher depth of cut, lower depth of cut, you will not hear any different type of sound from the machining zone. Why it is happening? Any deviation in the dimension of the setup probably too fine to any human tick, because it is difficult to find out those things. That is the reason the cost of the machine is so high that you cannot compare the normal CNC machine with the micro machine system. Why it is so high? Because you are using so many sensors there. Because these sensors should be reliable, so you cannot purchase a normal category sensor and you put it there. It is not like that. Even for using dynamometer or infrared sensor, the quality and the reliability should be so high that you ensure that at least for 4 or 5 years it should not create any problem. So to increase the reliability, you have to spend more time in money into the selection of the material, selection of the machining process. So all these things are add up in the final cost of the machine. So what things you have to remember during micro machining operation? First thing, the procedure for tool setup, tool length setting, and other setups are different. Even if you know how to operate a conventional CNC machine, you have to learn something extra in this case. A simple example, you understand that when you are doing machining in milling operation, conventional milling, what we do that we put a workpiece on the table, and then there is a vise. So what happens? We do that. Suppose this is the workpiece, and on this way we are putting a vise. Consider this is the vise, and on this side this is the jaw which is moving, and this is the handle. So when you rotate this handle, your jaw will move, correct, in this way. So what happened that once it is touching the surface, what we do, we provide lot of force here by hand force, and we ensure, just to ensure that workpiece should not move during the machining operation, right? So our objective is good, our intention is good, but the execution is wrong. Why it is wrong? Because when you are pressing these particular things too much, at that time material itself will deflect here. That means there is a internal deformation happens at this location, and that deformation is enough to create a problem in your micro scale. That is the first thing. Second thing is the tool setting. Consider that you are using a cutting tool here, and there is a tool holder. In the tool holder, you are putting the workpiece, you are putting the cutting tool. This is the cutting tool. Right? So there are three systems. One is the spindle, another is the tool holder, and third one is the axis of the cutting tool. Our objective is that all three should coincide. That is the thing. But we know that this is the mechanical assembly, so we do not expect that all the three systems should match with each other. So that is the reason that what is the minimum deviation which can be accepted. Right? So when you do machining operation, you consider the diameter is 100 micron. So this diameter is 100 micron. So thumb rule is that your run out should not be more than 10% of the diameter of your cutting tool. If it is 100 micron, your run out should be 10 micron or less. Correct? That is a thumb rule. But when you see at the lower scale, this looks very, very huge, considering 10 micron at a 100 micron. It is 10% is the deviation. Correct? So our objective that we let us reduce this thing to 5 or 1 micron. So 1 is the best, because it is very difficult to get run out less than 1 micron, because hardly I have not seen any tool holding system where run out is less than 1 micron. So this is the tool setup. Other setups are also there. What are the other problems? Now consider that you have a table, right? And on this particular axis, there is this particular is the overhead tank, and then overhead thing, and then there's the cutting tool and this thing. So on this table, what you do, you put this particular fixture. This is the tool fixture. And on the top, what you do, you put a workpiece and fixture. So this is the workpiece. Correct? So now what you do, that after machining operation, sometimes what happens that we need to do some type of reworking. Reworking in the sense that you move this particular tool fixture from one location on the location, something like that. So for that, what you do, generally what we do, that we slide over the surface, right? We do not actually pull back. That means you do not carry this thing over the surface and then you move. It is not like that, right? we slide it. So when you're sliding here and then, maybe thousands of times. If we are not talking that you purchase a machine and after 2-3 days you see, it is not happening like that. But since you have invested crores of rupees, you expect that your machine should work at least for 10 years, 20 years without any problem. But when you are moving this table thousands of times, what happens? There is a wear of these particular slides also. That is the base of the table. So when there is an uneven wear, at that time, because of the uneven wear, you are adding one problem, that is the straightness problem. And so that straightness problem will be added into the machine. So that is not acceptable. Right? So formula for machining parameters, rules of thumb, expectation, applying and average swap do not apply here. So what happened that you have to do some trial experiments to understand whether your tool will sustain the cutting forces and whether you are able to cut the material or not. That is the first thing, right? So in normal operation, what we have data books or PhD data books and machine tool data books are there. You know the workpiece material, you know the workpiece material of the cutting tool. There are speed, feed, and depth of cut data are available. These are highly optimized, and people are relying on those data. Correct? But the same thing is not available right now here. So what people are doing right now, people are working on a trial and error basis. They are generating lot of data, and we have to refer those data. That means if you see research paper, if you see some type of company brochure, you have to see that which parameter setting they have worked for a particular workpiece and tool material combination. And then you have to see that whether the same parameter settings are useful for your case or not. It may not work because the machine which they are using and machine which you are using, it may be different. If the machine tools are different, their accuracy, straightness, stiffness, everything are different. So sometimes what happens that even if you are repeating the same experiment on different machine, you will not get the same result. There are hundreds of other problems which are not visible, which are different from the earlier case. And successful results are never guaranteed. At the end, if you expect that if you do fast machining operation, you get the ready-made workpiece, that is not possible. Or not possible, that means chances are very, very high that you are end up with some errors. So what you have to do, that you have to do some initial cut on a small piece of the workpiece, and then you see that you understand how things are working, and then only you put the actual workpiece. Because sometimes the cost of the component is also so high that you cannot do trial and error on the original component. So you have to find out small components of the same material, and then you do some, or you can do some type of a practice, and then you find out the optimum parameters. And it is very difficult to understand how cutting tools are performed. That means cutting tools will perform. That is because cutting tool is so small that even small touch, unintentional touch is enough to break the tool. That because it is so gentle, it is so small, the stiffness is very, very low. A small amount of workpiece tool is here, and a small amount of bending force is enough to break from this one. So that is the problem of the micro cutting tool. And these are very costly. It is not like that is broken and you can purchase 100 other tools. So each tool is costing like a 3,000 rupees or 2,000 rupees. So that is also a problem. So sometimes several components needs to be machined to yield one acceptable component. Right? So you do machining 5-6 times, and out of 5-6 times, you will see that only 1 or 2 are acceptable. And that is the reason the components which are fabricated from the micro machining zone, these cost of those components are also very high, because they will add all these costs into the component. If all the components are coming as it is or ready to use component, then cost will go down because there is no rejection. So whatever is the rejection, that rejection cost will add into the component cost. So what are the important things which we have to look into in micro machining? So we already know that there are 3 main parameters of 3 components. This is the workpiece material, under is the cutting tool, and under is the machine tool. So these are the 3. So what are the things in case of workpiece material? Grain size is important, because bigger grain size, it is very difficult to cut. Smaller grain size materials are easy to cut. We will see in few slides. Hard materials plays important role, because harder material, that means if you cut a hard material, your tool wear will be very high. If the tool wear is high, then your sharp edge become blunt very quickly, and you cannot do machining further. Homogeneity is important. Defect, impurities, built up edge proneness, elastic recovery, these are the different. We will see some of the parameters in detail. Tooling, what is the material of tool? It is a tungsten carbide, it is a high speed steel. What is the material? Sharpness or the edge radius is important. Grain size should be very small, because your size of the cutting tool is 100 micron. So you consider that if you are using a tungsten carbide particle of a 50 microns. So in a one single tool, you have hardly 2 grain inside the material. So strength is so low. So you need grain size of a super fine grain size. That means less than 1 micron grain size is required. Then only you see the lot of grains are there and they can strongly adhere with each other and it will increase the strength of the cutting tool. Coating is required because coating is important to reduce the tool wear. But another problem is that initially your cutting tool is very sharp, but when you apply coating here, it is becoming blunt because coating will cover the sharpness also. So that also you have to see that this whatever you are losing the sharpness. This losing the sharpness should not be so high that it is end up with the blunt tool. Batch consistency, that means if you are creating 100 tools, what is the variation within that 100 tools in same batch? That is important. Machine tool spindle speed and run out is important. Run out, I already explained you that run out means how much is the deviation between the spindle axis and the tool axis. That is the thing. Spindle speed is important. Why it is important? Because you can see the simple example that you have a cutting tool of a 10 mm and same way you have a cutting tool of a 1 mm. This is the 1 mm. You both the things are rotating at 1000 rpm. Right? RPM is fixed. Now, what is the important parameter? Important parameter is the cutting speed. Right? So, cutting speed is variable here. Now, consider that when you will see that this particular location from this is the R and omega is this one, right? So, this whatever the cutting speed at this location, this is V equal to R omega. Correct? So, your cutting speed also depends on R. So whatever cutting speed you are getting here, suppose you are getting a cutting speed here 30,000. This is revolution per minute, and you put this particular 5 is the millimeter. So this is the pi. A roughly calculation is pi into 1000. And this is because in this particular case omega is equal to 2 pi n by 60. But roughly you can say something like this. It is a 500 millimeter per minute, right? So this is the cutting speed in the conventional machining operation. But what is going to happen in this particular case now, if you put R equal to 0.5 here, then it is very, very low, right? So to achieve this particular, this is the 5000 whatever you are getting here. So to achieve this 5000 in this case, what you have to do? You have to increase the RPM, right? Because your diameter is constant, so your R is constant. So which parameter is making difference in the V? That is W, that is omega, right? So you have to increase this RPM so high, then only you can achieve this particular cutting speed. So that is the reason in micro machining what happened, to just balance the, or you have to maintain the productivity or maintain the cutting speed, you have to shoot up the RPM like anything. Because reducing the diameter, you have to increasing the RPM proportionally to achieve the same cutting speed of the conventional machining operation. Position accuracy, that is, I already told you that it should be in terms of 0.1 micron or even smaller than that if it is available. Stiffness, damping, thermal stability, error compensation, these are the things which are required in the machine tool. If these things are not there, then you cannot do machining at a micro scale. So now what are the differences between the micro scale machining and conventional machining? So first thing is the grain size to chip thickness. Now you can see this particular slide. Here it is showing the conventional machining operation. So your cutting tool is moving in this direction and your chip is coming and is moving over the rack surface. So what these triangles are showing, so this is the size of the grain, right? So when chip is coming, chip is carrying many layers of grains. So these are the right? So these are many layers of grains are there. So you expect that most of the time deformation occurs at the grain boundaries. So it is very easy because if you see 2 grains are there, 2-3 grains are there, the weakest point of this between all these things are, this is the grain boundary. So that is the weakest point. If you want to cut the grain, then it is very difficult to cut the grain. Correct? So that is the reason that in conventional machining operation, most of the times your breakage or your chip will flow through this particular, it will break from the grain boundaries. Now coming to the micro machining. So how these things are different? This thing is different. Now, whatever we have done, that in this case, the size of the cutting tool we are keeping same. But if you see this triangle, earlier case, this was the triangle, but now we are entering in the grain. So what we have done, that the size of the chip is so small that all deformation takes place even in the single grain. So this is the single grain. So this is the single grain. So now what things we have changed? We have changed that our depth of cut is very small, and when you are going with a very small depth of cut, sometimes you have to cut the grain also. So that is the difference between these two and this. Here, many layers is coming out of this, and chances are either deformation or cutting will happen at the grain boundaries. But in this particular case, chances are very low that you will encounter a grain boundary. In place of that, you have to cut the grain. So that is the difference. Right, so shear deformation occurs within a single grain. That is in case of a micro machining operation. Stresses applied to the tool are dependent on the individual grain orientation. Right, so consider these are the two examples. Here the grain size is very big, and here grain size is very, very small. Correct. So now you consider this particular example, and your cutting tool is here at this location. Correct. And then what we do, we want to cut from this location. So this is our cutting direction. Same way here, our objective is to cut this material. So we are cutting from here. And our cutting tool is located at this location. Only difference is the grain size. Now let us see how this thing will behave. So when your cutting tool is moving in this direction, you can see that fortunately we are end up with the grain boundary at this location. But here in this particular case, you can see this is the big grain. Right? And cutting tool has to cut this thing to make it straight line. And now there's another grain. This is the big grain. Again, tool has to cut down this thing. And now, luckily, again, we get the grain boundary. So what is happening here? That if you plot the force diagram here with respect to this one, right? So initially when it is cutting, now consider that this particular location when it is cutting, at that time, no, let me draw it here. This way. This is the location, correct? So in this location, this is the F and this is the time. So when you are cutting here, now consider when you are getting grain boundary, your force variation will not be too much. So it is something coming like this, up to this, whatever it is showing here. So now as soon as you are encountering the grain where you have to cut the grain, so now force will shoot down like anything. Like because it has to take some additional load to cut the grain. And as soon as this is coming, now again you are coming with the grain boundary, so force will little bit reduce, and then it will go like this. So this is what is happening. Same thing here, if you see this thing, so here whatever the chances are very high that every time you will get the grain boundary. So because grain size are very, very small. So what is going to happen? Their force variation will not be too much. Right? So in this case, in a one particular bend, your whole force will move, but in when you are encountering very high frequency fluctuation of the forces, because you are rotating your cutting tool maybe 30,000, 40,000, even 1 lakh RPM, and you end up with this kind of a variation in the forces, sometimes very high force, sometimes very low force, that is not acceptable. So what is going to happen? That there is instability and instant tool breakage. So this is the effect of a grain boundary, or sorry, the grain size. So smaller grain size are very easy to cut, but bigger grain size you have to cut through the grain. Now coming to the minimum chip thickness. So what is the minimum chip thickness? That you might have encountered this thing in the conventional machining also. Now let's do a simple operation in the turning operation, that you go with a very small depth of cut in the turning operation. You will see that your tool is just rubbing the workpiece surface. It is not able to remove some material in the form of chip. Then slowly you increase the depth of cut, and then you see that whether at which particular instant you are able to remove material in the form of chip. So whatever that instant is, that instant is called the minimum chip thickness. So that minimum chip thickness is varying with respect to material. different material, different minimums on chip thickness. So that is the thing. So how this thing works, now consider this is the HM is the minimum uncut chip thickness or minimum chip thickness, whatever it is. And this is the set, that means whatever we are selecting. So right now, H is smaller than HM. That means whatever minimum in chip thickness there, you have selected something even smaller than this one. So what is going to happen? Your tool is not able to penetrate inside the workpiece surface. It is moving over the surface, but whatever material it is deforming, that material is again resurfacing from the deck side. So that is called elastic recovery. So your overall work is zero, right? Because in machining, our objective that it should come, it should remove the material in the form of chip, but here nothing is moving. Whatever it is moving over the surface, the material is little bit deforming, but again it is resurfacing from the bottom surface. So that is not acceptable. So now what we have to do, we have to increase this, or you have to reduce this particular, we have to increase this particular HM. Right, so now second is the, let us keep both are same. Our set depth of cut is same as the HM, minimum uncut chip. So now something is improved. What is improved? That now something is coming out in the form of a chip. But still there is a problem. Some material is there which is again elastically recovering. That means whatever depth of cut, this red color dash line is there, all material should have been removed. But that is not happening here. Something is removing, maybe 50% is removing, 50% is coming as elastic recovery. So still this is not acceptable. So again, let us move a little bit more. Now our H is higher than HM. Right, so this is higher than that. Now what happened that all the material, whatever this baseline material, everything is coming out in the form of chip, and now you are getting a plane surface, no elastic recovery at this location. Right, so this is what is acceptable. But what is the problem that if you do not know this particular setup, that what is the minimum uncut chip thickness for a particular material, and you do operation in this, and this is obviously the most disastrous. That means you are not going to get anything at the end. Your workpiece will be as it was earlier. In this case also it is disaster. Why it is like that? Now consider that you have a workpiece. Correct? You are doing machining operation and you want to do 3 cuts here. This is the first cut, this is the second cut, this is the third cut. All 3 cuts have the same depth of cut. Correct? So like consider that every time we are giving 100 micron depth of cut. Here also 100 micron, here also 100 micron, here also 100 micron. You are doing machining first time. So let us complete the first part. Correct? So first part is over. First part is over, but problem we know that in this case there is something is removed, something is still recovered. Right? So when you are cutting with 100 micron depth of cut, for this 100 micron depth of cut, you have selected speed and the feed rate also. That is F and whatever you have selected, that you have selected considering that you are cutting 100 micron depth of cut. Correct? So that is the setting. When you complete the first part, you expect that your 100 micron is removed from this. So you go with the same set of F and N and you want to cut the second part. Problem is here that it has not removed the 100 micron, it has removed 50 micron only, considering the 50% recovery. So what is going to happen? The when you are cutting the next part, you are not cutting 100 micron. Basically, you are cutting 150 micron, right? Because 50% is what it is recovered from this thing, and now you do not know this thing. And when you are cutting 150 micron with a set parameter for the 100 micron, your tool will not work. Your tool will be broken, right? Because each and every set parameters are basically for the particular depth of cut. Now your depth of cut has changed, but you do not know that it has changed because this information is not available beforehand. So you continue second part, as soon as it is touching the surface, forces are so high that your tool will be broken. So that is a problem. Right, so now coming to the defects. Now we know that no material is perfect material or the ideal material. Right? There is always some type of defects, impurities, grain boundary problems, many things are there. So what is the thing that these are basically helping in the machining operation, because these are the weak points. These are called the soft points. So if your tool is encountering this soft point, your forces will be very low and your tool can easily pass through this thing without any problem. So sometimes the defects are helping in the machining operation, but that doesn't mean that you introduce intentionally some defect, right? That is not acceptable. These are inherent defects where you are not introducing, but these are contained inside the material. So plastic deformation usually starts from the area where defects are there. Then dislocation, inhomogeneity, these are the defects. Now what happened that if you have material and if you are reducing the size of that material, right? That means that if you are reducing the size, your defect level will also reducing, right? Because you are going very small. So right now this is the area. Then slowly you are reducing the area, and then you are reducing area so low the number of defects are very less. So what happened at this particular location, your material start behaving like an ideal material. That means almost free from the defects. So if defects are not there, then from where will you get this particular plastic deformation initiation? Where you will get the easiness of the material removal? So that is a problem. So material resists the plastic deformation much more strongly than expected due to the less defect, because now material resists very quickly because it does not have any type of defects, or level of defects is so low that these micro cracks and all these things are not possible to get very easily. So that is the reason your defect level will be lost. So small depth of cut, deformation will happen at a small scale, and when it will happen at a small scale, you are getting the less defects, and when the defect is very, now your tool will encounter more force as compared to your conventional machining processes. So there are two problems. One is the tool is very small, so its own strength is very less, and another thing, addition to that, the material response is also very strong, so your tool will be broken very quickly. Now coming to alloy. So alloy has also its own story. Right, so what is the alloy mean? That means there are two phases. One is the hard phase and there is soft phase. So same thing happens here. When you are cutting alloy, now you consider you are cutting from here. So at one location, this is the soft phase. So you again draw the force diagram. So in this particular location, you will get very less force here. And as soon as it is passing through this hard phase, at that time you have to cut this hard phase. So your force requirement will be very high. Again, a small area is coming in between these two, the force will be reduced. Again, force will jump like anything, and again it will reduce. So this variation of the force is not acceptable. So that is the problem when you do cutting of a alloy material. So what parameter you have to set? You have to set the parameter considering that all material is the hard material. Right? Because at the higher setting, you can cut the soft material, but you cannot cut the hard material at a very nominal setting. So that is we have to look into when you cut the alloy. Now coming to the specific cutting energy. So we know the specific cutting energy, that means energy consumed in removing a unit volume of a material. That is a simple definition. That definition also coming in this case also. My comment that is applicable. So if you are doing a orthogonal cutting operation, then we can know that Fc into V is the energy, and then it is the unit volume is the BHC in the V. So this is the cutting speed, then it is HC is the depth of cut, and B is the width of the particular workpiece. So from there, this V will go, and your specific cutting energy function of the cutting speed divided by B into HC. So consider that when your tool is moving, the whole B is coming into picture. So your B is also constant. So only variable is the FC and the HC. HC is the depth of cut, and FC is the cutting force, what is required here. Right? So now what is, we have to understand that when you are cutting something at a very small scale, your cutting speed, specific cutting energy is very high. Why it is like that? Right? So let us see. So when you are doing machining operation, now simple logic is that if your depth of cut is small, your forces are small. That is obvious because your tool does not need to remove too much of material. But if you give high depth of cut, your forces are high because it has to encounter that much amount of resistance from the workpiece. So it has to remove that much material. So this is simple logic, or it is also acceptable. The smaller depth of cut, smaller is the force. But how long this particular relation will maintain? Right, so this is the diagram. So this is the depth of cut. And this particular axis is showing U and F both, FC. This is the same guy. Right? So now what happened that this particular location. Let us target this one. So whatever HC is there, now you can see this particular diagram. What we are doing, we are reducing this HC from this value to this value. So you are reducing this HC, and when you are reducing HC, your FC is also reducing, because we know smaller depth occurs, smaller force, right? So ultimately there is no difference in the U, because denominator and numerator both are reducing. So you are getting a no variation in the U. So this is the U. But what happens that after you cross a particular limit here, what happened that it should continue like this. This line, it is showing that if you are maintaining this correlation, smaller depth of cut equal to smaller force, it should follow this thing. If it is following this thing, then your U should also come follow this thing, like this one, because both are changing. But it is not happening like that, because after a certain value of depth of cut on the lower side, we have seen that your defect level is reduced, your material strengthening is happening. So now what happened that your force requirement is little bit shifted. So this is your force requirement now. Because of this, what happened now that HC is reducing continuously, but now FC is not reducing the same way it was earlier reducing. So its reduction in the F is little less. So now because of that, what happened that your cutting, specific cutting energy is shooting like anything. Why it is happening like that? Because your HC is in micron, right? It is 10 raised to minus 6, whatever we are giving here. So when 10 raised to minus 6 is going from denominator to numerator, it is coming with 10 raised to 6. So this is very, very high. Consider. So in this case, whatever is this difference, this from here to here, this difference. So this difference is responsible for very, very high cutting, specific cutting energy, right? So it is written the cutting force does not tend to continue to decrease as the uncut chip thickness is reduced. So earlier it was something moving like this. So that is the reason we got a straight line. There is no change in the U. But as soon as it is crossing one particular limit, there is a problem. So FC levels of below a certain range of SC. So that is the range. So from here, that proportionality is lost completely. And that is the reason FC does not decrease proportionally to HC. And that is increasing the U dramatically. So that is also a reason that why it is happening. So now consider that to get that particular HC, what you have to do, right? So now consider whenever we are drawing one diagram of a cutting tool, we draw something like this only, right? In a simple merchant cylinder diagram also, when we are showing, we show a cutting tool something like this only. But we do not see that none of the tool is sharp like this one. If you magnify this thing, you will see that there is a rounding edge. So this particular thing is called the cutting edge radius, right? So in actual case, this is called the sharp tool, that what we draw. But in actual case, what happened? This is the blunt tool. Blunt tool, that means there is a finite radius is there at the end, right? So cutting tools are never perfectly sharp. Cutting edges is never as a ideal straight line. So these things are not like that. There is always a blunt tool. Blunt tool means there is some finite radius. So when HC becomes comparable to the cutting edge radius, so this is considered HC is there. Now you have something like this. This particular thing is the cutting edge radius, correct? And then you have workpiece. This is the workpiece. Your tool is moving in this direction. So this particular thing is FC, correct? So now you can see that this RC and HC both are comparable. Right? So this is also a problem. What is the problem here? Because now you can see that to remove this material efficiently, what we have to see that this HC, that means the minimum uncut chip, your set depth, uncut chip thickness, set depth of cut should be higher than the minimum uncut chip thickness, right? That we have seen it should be higher than the HC. Then only it will remove the material. But that is not the end of the story. You have to also see what is the sharpness of this cutting tool, correct? So now if you see both things are comparable, HC and HC, that means it is like that you are cutting a vegetable using a blunt knife. That is what is happening. So for doing this thing, your material removal will not happen very, very easily. So there are two ways. One of the ways is that you increase the HC. So you increase the HC something like this. So then you will be able to remove the material. So HC is now this much. If you do not want to do this to reduce the forces on the component, because now if you go with higher HC, your forces will be very, very high and your tool may be broken. If you don't want to go with this option, there is another option. You make your cutting tool sharp, reduce this RC. If you reduce the RC, again you will get this HC higher, so that is acceptable. So what we need HC should be higher than RC. Right? So depth of cut should be higher than the cutting edge radius. If this thing is not fulfilled, then again there is a problem in the machining. Right? So this is which location you end up with this one. So this is the location of R where at this particular location, that is the location of the cutting edge radius. So when you are working with this particular cutting edge radius and you consider that you are continuously reducing the HC, whatever diagram I have shown you earlier, this is your cutting tool. So this is your HC, and something is here that is called RC or R, whatever it is showing here. So now what we are doing, that we are reducing this HC continuously from here, something like that. So at one particular instant, what happened, that it will encounter the value of RC here. So whenever it is reducing to this level, now what happened, that your cutting edge radius is comparable with the depth of cut. So then it is the reason that your specific cutting energy is increasing, because now your tool is not considered a sharp tool, but it is considered a blunt tool. And then blunt tool is removing the material and it is taking more time or the more energy. So that is the reason that HC becomes comparable to this one, and then you end up with the more amount of forces. So now coming to the specific cutting edge. So this diagram is very well known and many people are using this diagram. So let us see this thing. So now here it is showing the resisting shear force, shear stress. That means how your material will resist the deformation when you want to cut. In this section, it is showing the chip thickness. What is the size or chip thickness of the machining? So if you start with this particular multi-grain, that means the number of grains are very large. So that is in terms of tension test, turning operation, that is a conventional machining operation. And when you want to reach to this precision milling, that means micro machining operation, and we have seen that deformation starts from the weak points. So what are the weak points? Weak points are the grain boundaries. If you look at the grain, so when you are doing machining operation at this location, considering like a 10 micron depth of cut, at that time, what is going to happen? The grain boundaries and the cracks inside the grains, these are the weakest point, and that will become the part of the location from where the material will be deformed. So when your HC is more than 10 micron, grain boundary become the origin of the breakage. So let us reduce it further, going on the downside. So now we have reduced it further. Now it is at this particular location, like at this location, it is a 1 micron. So here what is going to happen, that when it is reducing like this, so now you are entering, because now reducing this means you have to cut the grain. So when you are cutting the grain, now you have to find where are the problems inside the grain. Correct? So there are problems inside the grain. These are the dislocations within the grain. Now you can see that this is the grain. So in between the dislocation, distance is 1 micron. So now we are cutting at a 1 micron. So we have to see what are the problems inside the grain. So every time we have to find weak points. So what are the weak points? Weak points is dislocation. So it is trying to find out where is the dislocation, and it will cut the material. Right? So let us further reduce it. So we are reducing it further down to this one. So at this particular location, dislocation becomes the origin of the breakage. Further defect, you go down. So now you are entering inside the dislocation. So for what? You have to find out what particular thing. So these are called the interstitial vacancies are there. So now you have enter inside the atom. So now you have to see the atomic structure, deformation. What are the point defects are there? What are the vacancies are there? So it is trying to find out those weak points, and then it is becoming the point defects becoming the origin of the defect. So now consider that going down and down, you have to find out where is the weak point. That means material will find out. You don't need to find out. Wherever the weak points are, your tool will cut down that material. So this particular depth of cut, what we are looking at, this 0.5 micron or something, that much depth of cut we generally do not give in the micro milling operation, but we give that depth of cut in the diamond turning operation. So that itself is a under process, but it is called like a precision machining rather than the micro machining. So that is the reason there is a differentiation between the diamond turning operation and the mechanical micro machining operation. So understanding from this graph is that it is very easy to material if your cutting tool is encountering defects, whether it is income defect at a grain level or it is getting the defects at the atomic level. Everywhere defect is the important thing to cut the material without any hike in the force. Now coming to the burr formation. So now what happens that in micro machining or bigger scale, it is difficult to avoid the burr formation, right? Because burrs are always formed. So these are the burrs. You may get a top burrs also, entry burr, exit burr, side burrs, many things are there. But advantage of the removal of this burrs in the bigger component is that it is visible. You can see easily all the burrs and you can easily remove those burrs also without any problem. There are many processes are there. Problem of the micro burr formation is that component is also very delicate. The visibility of these burrs are very low because you do not know from where you have to remove the burrs. Even if you apply some deburring operation, correct? So visibility is less, material is very, very gentle in the sense that even if you apply some deburring operation which you are using for the conventional machining, sometimes it will damage this particular component also. Right now, whatever the straightness and these things are visible, it may increase also during the aggressive interaction. It may damage some other features also. So you cannot remove these burrs very aggressively in the micro machine component. So you have to find or you have to devise some methodology or some methods by which you can remove these burrs, or you can minimize also. So what are the problems because of the burr formation? Many problems are the improper part mating, because now you can see that if some burrs are there, this is the component, right? And some burrs are formed here at this location. And now there is another component, something like that, which you want to enter inside it. But when you are putting inside it at them, this burrs will not allow to match this particular edge and this edge, because this burrs will create problem in the assembly. Dimensional inaccuracy, that is known, because sometimes if burrs are there and if you take that thing as a reference for measurement, then your whole measurement system will be wrong. Surface finish, it is obviously high, because high burr formation that will end up with high surface roughness. Increase the cost of the production, because this removal of the burrs, it is considered as a additional process, means there is no productivity involved in that. It is additional process by which you want to remove. So that is an additional step you have to put into the machining process to remove this unwanted material. So that is additional cost and the time both. And accelerated wear in the device, because by chance if you use a component with the burrs, and that burrs during the operation, suppose this burrs is dislodged from the original component, and from that burr, whatever is removed from the component, it will become part of the component, it will remove the other unwanted material. So simple example, you can see that these are the two plates, and in the bottom plate there are some burrs are there. So when these burrs are there, and when this plate is coming in contact with this thing, and when it is moving, at that time what happens, that the burrs whatever are there here, at that time this particular top plate will remove this burrs from this. This means burrs will be detached from the original component, and then it will move here and there in between. So when it is moving, at that time it will start removing material from both the surfaces, top surface and bottom surface. Then the clearance will be increased, and at the end it will end up with the accelerated wear. So it will start wearing both the components, base component as well as the counter body. And decrease the device point. That is understood, because this device will not work when the burrs are present into the system. What are the processes? 6 physical processes that I will show you here. One is the lateral flow of the material which occurs, because when you are doing machining operation, at that time you are pressing your cutting tool into the material, and there is a chances are that material will flow around the tool also. Bending of the material, because at the very small scale machining operation, chances are either your workpiece will be bent, and there is a problem. Tearing of the workpiece from the workpiece material, chip from the, because at the end when you do not get any support from the workpiece, at that time your chip will be teared off from the surface. And sometimes because of the elastic recovery and anything, some material will redeposit onto the material surface. An incomplete cutoff, that means you are starting machining from here. Your objective is that your tool should completely move from the surface, but because of the problem in the part program, your tool is reaching here and then it is coming out. So whatever material is left here, that material may be considered as a burst. And flow of materials into the plate. So these are something at a very, very micro scale. Visually, you cannot see this thing, but when you observe any machine component microscopy in the SCM, scanning electron microscopy, or other very high-end magnification equipment, you will understand all these things. So factor of burr formation, the tool sharpness is important, because higher is the sharpness, lesser is the tool formation. Workpiece material is playing important, but by workpiece material you cannot avoid the burr formation. Feed rate is important. Higher feed rate will give you very quick material removal, but on the same side, by pushing the tool too much high also, it will bend the cutting tool. Then the chances are high that your cutting tool will be broken. Cutting speed is important. Higher cutting speed is it is recommended. Chip thickness should be also little high. That means you have to maintain that uncut chip thickness ratio and cutting edge radius ratio. Then you can get this thing done. Now coming to this up milling and down milling operation, because when you want to cut a machining channel inside, you end cut up milling and down milling, both things will happen on the same component. So on this particular side, it is called the up milling, and on this side, it is called the down milling. So what is going to happen that when you do machining by this way, you are getting more smaller balls on the up milling than the down milling. So this particular case is called the up milling, and this particular case is the down milling. This is down with this particular thing down. This is called up milling. Why it is happening here? Now you consider that your tool is moving from here. So this is your cutting edge. Right? So cutting edge, when it is penetrating inside, it is collecting the material, right? And when it is rotating complete, it is throwing the material on this direction. And at the same time, it is moving also. So whenever it is throwing material on this direction, at that time, what happens that whatever is collected from here, something like this is your cutting tool, and this is moving in this direction. So it is collecting all the material here, and then it is moving here, and then it is throwing this material here. So when it is moving in this direction, at that time, it does not have anything which is further remove the material. So this all the things, if something is left, that will be deposited here. By chance, some burrs are formed here at this location, but this tool is moving in this, and at that time it will collect this material, and then it will move in this direction. So that is the thing in case of a up milling and down milling. So now what is happened if material is ductile? You have high elastic plastic region of deformation. That means your material can elongate more. Right? So at that time, a large burr formation are expected. If material is hard material, that means burrs will be less because your elongation of the material will not be too much. But there is another problem. If the material is hard, there is a more tool wear. If the tool wear is more, you are end up with the high cutting edge radius. High cutting edge radius means negative rake angle, flowing, and then again more burr formation. So whether you use a ductile machining material or hard material, you will always end up with the burr formation, because you cannot escape from the burr formation. So how you can remove them means what are the strategies by which you can remove this particular burr or you can avoid burr formation? One is using the supporting material. Suppose you want to avoid the burr formation at the end. So what you do that you put supporting material here, you continue machining like this, and whatever burrs are formed, that will be formed on the supporting material. And then at the end, what you do, you remove the supporting material. So your component will be free from burrs. That is in case of a entry burr or the exit burr. What is going to happen for the top burr formation? Same thing you do. You deposit one supporting material on the top. You do machining, but during machining, you have to make sure the depth of cut should include the thickness of the workpiece, this deposited material. Correct? So your workpiece is this one. You want to do machining like this one here. Right? And now you put or deposit something like here. So now your tool should enter up to this. Correct? Then only it will remove this all the materials. That means you are doing during original machining operation, you are machining this particular supporting material also. Correct? So once you complete the machining operation, machining will be done on supporting material also, then you remove the supporting material, your workpiece will be free from burn. So these are the different strategies. The processes are many. Electrochemical polishing is there, powder blasting is there, micro pinning, means ultra sonic wet pinning is there. Micro EDM is also used because it is a free force-free machining operation. So that can be also used for deburring. And many gentle polishing processes are there. Some of them we are also using for micro burr removal. So let me finish this class here. So I think I have taken enough time. And if you have any questions, I am happy to answer.
Thank you, sir.
Yeah.
Sir, shall we go with question and answer session, sir?
Yeah, sure.
Yes, sir. One question from chat box, sir. Shall I read it, sir?
Yeah, sure.
This is from Professor Yogesh Dubey. Sir, can you suggest the type of device or thermocouple which is useful for measurement of temperature near the micro machining region?
So in this case, what we do not use thermocouple, because when you are using thermocouple, you have to drill a hole to very close to the machining zone, and then you have to also ensure that thermocouples are retaining their position for that location. So what we do here, that when you want to do measurement of temperature here, we generally use some infrared cameras. And for in machining also, because here what happened that your thermal softening is not too much, because when you do machining at a micro scale, your depth of cut is also itself in the micron level, maybe 10 micron, 20 micron. So temperature rise in the micro machining is very, very low. And sometimes your thermocouple cannot detect that much small changes. So that is a problem. So if you see this micro machining operation, and if you see papers on thermal modeling, you will find most of the time they have done simulations only, because it is very difficult to get the actual thermal reading, that is temperature reading in the micro machining job. So that is a big problem. So there are very less amount of papers, because even if you try to attempt that thing, you do not sure that whether the result is acceptable or not. That means it is correct or not. So generally, people do not work on the thermal modeling, thermal aspect of this machining, because it is very, very difficult and it is not reliable also.
Thank you, sir. The second question from him: which type of machine is suitable for micro machining in steel, and suggest cooling media also, sir?
Because here in steel cutting, what we do, that we, whether it is steel or it is a aluminum, brass, we always use tungsten carbide, because these tools are readily available. Even India also, some companies say that micro tools, they are fabricating cutting tool at least up to 100 micron tool. So on any material, we are using my tungsten carbide only. So if people are using some type of a diamond coated also, but if you do diamond coated tools, then the size becomes a little bit hard and you cannot get the sharpness and everything very quickly. So for that, and cooling media, they are using some proprietary, because what a current machine we are using, they have suggested some one grade is, I forgot the name, I do not remember the name, but they have some particular viscosity grade, because they make sure that we have to use that only. If you do not use that thing, that means your warranty is void.
Thank you, sir. This is another question from Professor Apollo Naidu. Can you suggest nature eco cutting fluid for machining hard materials? Present using cutting fluids are not safe.
In this case, what we do, that generally when we want to do some fundamental study, that means cutting force measurement, everything, we do not use fluid at all. Because what happened, that our dynamometer, whatever we are using for force measurement, is so sensitive that even the impingement of the jet will also create one additional force signal. And the force signal actually generated from the machining, it is also very weak, that it will couple this actual machining signal as well as the force generated by this cooling, that will also generate additional signal. So at the end, you are getting some results which is mixture of this thing. So it is very difficult to find out what is the actual signal. So when we do fundamental study, we do not use cutting tool at all. And when you do want to do some type of product-based machining, at that time, what we do, we use mist coolant. So mist coolant is basically droplets of this particular coolant that is impinging on the surface, not exactly surface, but we have to make sure that it is targeting the interface. Interface, that means the tool and the workpiece contact point. So tool should be loaded with the chip also. So we do use the mist coolant. We do not use flood coolant here. And for that also, that proprietary that coolant is there. But if you read the papers, you will find out name and everything. So I don't remember the name of that particular coolant. But even the eco fluid also, if you see some paper that MQL, the minimum quantity lubrication and eco fluid, there you will find at least 20-30 papers where people have used some type of a vegetable oil and mixture of different things. So there are n number of options available. So right now, which one is good, that I do not know.
Thank you, sir.
Yeah.
I request dear participants, you can unmute yourself. You can ask directly, ask question to our resource person, or you can type your question in the chat box.
Sir, Rajesh here, sir. Rajesh from SV College of Engineering, sir.
Yeah, please.
Sir, can we able to mount a micro cutting tool to ordinary conventional machine tool, sir? Is it possible?
You can mount. Mounting is not a problem because all the micro cutting tools, they are coming with 3 millimeter of Cheng diameter. So 3 millimeter Cheng diameter is more than enough to hold any cutting tool. But problem is not the holding. Problem is whether your cutting tool will work in that machine or not. So simple measurement is there. That after putting your cutting tool into the tool holder, you just measure the run out.
Okay.
You use the dial gauge.
Then, please, sir, please.
So you get the dial gauge and you rotate your cutting tool by your hand and see that what is the movement of the dial gauge. If the movement is more than consider the 10 micron, 20 micron, that means it will not work.
Okay, sir. Then what about that cutting speed, sir?
Cutting speed requirement is very, very high. Because what we do, we have cut some type of PMMA sheet and everything like a 3000 RPM also. 3000 RPM and diameter around 200 micron. But it is not very efficient. And for that, our corn machine has a speed of a 50,000 RPM. So even the 50,000 RPM also sometimes does not work. But I have reported, some reported papers are there where the spindle speed around 2 lakhs RPM. That means in 1 minute is rotating at a 2 lakhs rotation.
2 lakhs.
So higher is better. In this particular case, higher is better.
Okay, sir. Thank you, sir.
Thank you, sir.
Yeah.
Dear participants, I request once again, if you are having any doubt, you can unmute yourself and you can ask question directly to our resource person. Or you can type your question in chat box. We will read on behalf of you. Sir, it seems no questions.
Everybody understood, or probably everybody do not understand?
No, it is very nicely explained, sir. Everybody understood. So just we are going with the vote of thanks.
We are getting feedback, sir.
Yeah.
Nice feedback. Excellent.
Okay, then it is not a problem.
Just 2 minutes, sir. I will go with vote of thanks, sir. Thank you for your wonderful presentation, sir. Your presentation added more value for this short-term training program. Really, it is excellent presentation, sir. You have given good knowledge about mechanical micro machining, which are useful for all the participants. The takeaway from your presentations are very high. You have started with mechanical micro machining. It is a not independent process and important in efficient and accurate cutting. Basic concept in machining. Machine tools are subject to errors, forces generated by machining, weight of structural elements themselves, and high precision micro machining centers. And CNC milling machine, you have given the comparison between conventional CNC and micro machining, and micro machining applications like tissue removal tool, dental bracket, MTD micro molding, biomedical and biomems, watch-based press, ornamentals, micro machined transducers in automotive, aerospace applications, miniature device for brackets, micro turbine, electronic components for measuring devices, and atomic material sciences. Operator skill and sensing in micro machining. Manual skill are very valuable, you told, and predicting how cutting tools will perform is often impossible in the micro machining. Sometimes several components to be machined. Key aspects in machining you explained, like work material, tooling, machine tools, and difference between macro and micro machining explained, and material behavior at micro scale machining and alloys, specific cutting energy in detail you explained. Finally explained factors for burr formation, in up milling and down milling and material properties and burr control by support materials and deburring process. Thank you very much, sir. Really, it is excellent presentation, sir. And now
Thank you very much.
now I request our convener to conclude this session with the thanks to our resource person, sir. Requesting, sir.
Sir, is it audible?
Yeah.
Yes, sir.
Yes.
Yes, sir, please.
Good afternoon, sir. This is Dr. M. Chandrasekhar Reddy, convener of this program, sir.
Yes.
On behalf of management, principal, Department of Mechanical Engineering of SVCE and participants of STTP, thank you very much for accepting our invitation and delivering an informative and thought-provoking webinar on mechanical micromachining organized by SV College of Engineering, Tirupati, in spite of your busy schedule, sir. Thank you very much, sir. And
Thank you very much.
I'm also thankful to the Dr. Ravi Shankar, sir, who has given your
No problem. We know each other since a long time.
Yes, sir.
Yeah.
Thank you, sir.
Okay.
Excuse me, sir. Thank you, sir. One more last question, sir, in chat box. Is metallurgical changes is more in micromachining than conventional machining?
No. Here hardly you will get changes in metallurgical because forces are so low, temperature generation is also not there. So there is chance, means almost zero chances there will be metallurgical changes. Conventional machining is very aggressive. At that time you will find lot of residual stresses and other changes. So here means you forget, means there is nothing, no changes will be there in micro machining.
Thank you, sir. Thank you, sir. Thank you very much, sir.
Yeah. Okay, then I am disconnecting. Okay.
Thank you, sir. Thank you.
Okay, bye.
Dear participants, tomorrow at the end of the afternoon session, that is tomorrow we are having afternoon session, 2 resource person here to come. After the last session, you will receive final assessment link. You need to achieve minimum 40% of mark to receive the participant certificate. This assessment link will exist up to 6:30 p.m. sir. And the questions, for example, it will come around 25 questions. So once you have solved, you will get automatically a participant certificate, sir. And tomorrow morning session is from Professor Salim Basavarja Salimat from a company from Textual Brothers Private Limited, Bangalore. Topic: recent advances in atomic force microscopy by Oxford Instruments. Our morning session starts exactly at 10 p.m. Please, I request all the participants, please join in 9:45 a.m. itself. Our morning session starts with 10 a.m. Please, I request all the participants, please join 9:45 a.m. itself.
So in the morning
And
session,
our
Madhivanan sir,
yes,
just some
yes.
clarification.
Yes, sir. Yes, sir.
In the morning session, there are 2 sessions are there. One is by Basavaraju Garu, and other one is Soundar Pandan. There is a small mistake in this slide.
Okay,
So,
okay. Okay, sir.
11
Okay, sir.
o'clock. 10 to 11 is Basavaraju sir. And
Okay.
11 to up to 1 o'clock, you may give Dr. Soundar Pandan, who is a scientist. Now he's working with the Government of India, Minister of Electronics and Information Technology in New Delhi. So he's giving at 11 o'clock. And the last afternoon session is again Dr. Ram Prabhu, sorry, scientist DRDO.
Okay, sir. Thank you, sir. Thank you. Thank you, sir.
So after these 3 sessions, they are going to get final assessment and final feedback. Okay, so that's what you have explained. Minimum of 40
yes,
of marks they have to get. So that questions
Yes.
are very, very simple. If you have cleared all the sessions assessment link, from that assessment only you are going to get that questions again.
Thank you,
Any
sir.
doubt, please.
Dear participants, if you need any clarification,
regarding this, you can ask us.
Yes. Our afternoon session ends here, and tomorrow morning session, as usual, 9:45 a.m. Then you can good to start at 10 a.m. I request all the participants to join 9:45 a.m. itself.
Tomorrow, don't miss the afternoon session and morning session. Morning session, Saundar Pandya sir is going to tell you what are the scopes of funding also, because he's working in Ministry of Electronics and Information Technology. What are the funding agencies also is going to tell. Okay, apart from this title, IoT.
Okay, sir. S- Sir, Professor Subbareddy, what is the time of the test, sir? After the vote of thanks, tomorrow afternoon session, after the vote of thanks, we will give the assessment link, and that link will be exist up to 6:30 p.m. You can finalize the link and you can send it, sir. Immediately, you will get the certificate also.
So without tomorrow's feedback and assessment link, you are not going to receive any certificate. This is for your kind information. Please coordinate with that.
Dear participants, the assessment link will be given in Google Meet and YouTube link only. It will not be given in WhatsApp group. Kindly make a note of it.
So if required certificate, so you have to attend tomorrow without fail. So it will the Google link, that's assessment link and feedback link will not be shared in WhatsApp or mail ID. Okay. Please cooperate with us because it is a must for us to submit the AICTE. The feedback and also the test. That is assessment tomorrow.
Charan sir. Charan sir. Yes, sir.
Yes, madam. Go ahead,
Sir,
madam.
yes, 4 to 6:30. Actually, during that timing, I'm in traveling. I'm leaving my campus. Yeah.
Okay, ma'am. Ma'am, just you send some 10 minutes, ma'am, so that because if we are losing the time, no, it is very difficult, ma'am. Otherwise, we can take extend up to 7 o'clock also, no problem.
Yes, sir.
4
Surely.
to
I
7
don't
p.m.
want to miss that because see, my college it will over at 5:30, and I will reach at home at 7 o'clock. So
Okay, okay, ma'am.
5 o'clock I'm in traveling.
Okay, you can, ma'am,
Madam,
up to 9
madam.
o'clock it will be, ma'am. No problem, please.
Okay.
Okay. Okay. Thank you so much, sir. Yes.
Okay, thank you, ma'am. Thank you.
Madam, Poonam, madam, please mute your mic, madam. Thank you, madam.
Sir, today feedback link just now posted and it has posted many times, sir. Please identify, sir. Dear participants, our today's session ends here. Tomorrow we will meet once again. Thank you. Thank you for all.